Welcome to this webinar organized by CROSSBOW project, funded by the Horizon 2020 program of the European Commission. This webinar introduces one of the products of CROSSBOW, which is the Storage Regional Coordination Center. There are mainly two partners from CROSSBOW project leading this product, University of Manchester and Varta. University of Manchester as a product leader and developer, and Varta as a work package leader coordinator.
So the modeling of STO-CC is mainly represented by the figure in the left-hand side. So STO-CC algorithm receives the required data to operate from two main sources. Each source captures, produces, and provides the data in a different manner and format. The first involves the data related to the storage system, which is represented by the energy storage and unit and hydro pump icon in the figure, whereas the second source includes the data regarding the status of the network, which is provided mainly by a web protector. Then the figure in the right is how the user interface displays this information. So, for example, in this case, the state of charge of the pump hydro storage can be seen, and this allows us to use this data as an input to STO-CC to try the different functionality that we will discuss in the next slides. This is the equivalent network that we use to implement STO-CC. So in the left hand side you have the Serbian network, where most of the renewable energy comes from the north part. In the right hand side you have the Bulgarian network, where also most of the renewable energy, which is wind and solar, come also from the north part. Both networks are interconnected with just one tie line, which is between bus 50 from the Serbian network and bus 33 from the Bulgarian network. The voltage level is 380 in the Serbian network, whereas in the Bulgaria is 400, and 220 kilovolt in both networks as well. So here we can see the result of modeling STO-CC. 4 different functionalities were developed for implement STO-CC. So in this case, we are going to describe only 2 of them. So the first functionality is the command dispatching to a storage unit. So the figure in the right hand side on the top that show the level of rest curtailment when no storage and national storage and regional storage are used, whereas the figure on the bottom use the level of penetration when exactly same conditions are considered. So as it is expected, the highest level of rest curtailment, which is represented in the top figure by the blue line, is achieved when no storage assets are used. So once the STO-CC is applied at the national level, which is represented by the black line, a significant reduction of rest curtailment within the Serbian network is obtained. Now, this reduction is even bigger when the Bulgarian system, which is represented by the regional storage, is used to model STO-CC. So, as you can see in this figure, the largest amount of rest curtailment is when not storage is used at all, but when the regional storage is used, we have a very amount of rest curtailment, and this can be validated in the figure on the bottom, where the highest level of penetration of rest is when the regional storage system is used, whereas the blue line, which represents no storage at all, the level of penetration is quite low. The second functionality that we're going to present for STO-CC is the network congestion mitigation. So the national storage unit is used first to store the surplus of renewable energy. This is represented by the blue bar in the top figure. So when the The Serbian network represents the national storage system, whereas the Bulgaria is used to represent the regional storage system. So when the Serbian pump hydro storage is close to its capacity, the Bulgarian storage system begins to store the excess of rest that cannot be stored locally, and this is represented by the green bar in the top figure. Then, when we implement the line congestion management, which can be seen in the bottom figure, at the national level, which is the graded blue bar, it can be seen a reduction in the stored energy nationally, whereas the regional level, with the inclusion of line congestion management, the energy stored increases, and this is because the rest exceedances caused by the implementation of the line congestion management at the national level grow, and therefore more storage capacity is demanded regionally. So as a result, the regional storage units, as the case of Bulgaria, access is more utilized.
Hello everyone, so let's talk about the potential end users of STO-CC. Potential end users mainly include system operators, so the TSOs and the DSOs, storage owners, and energy producers. The scope of end users might be extended and include general electricity consumers who own storage devices at their residence and have contract to deliver services to the power networks. So, what will be the application of STO-CC? For system operators, STO-CC will provide system-level services respecting grid technical requirements. These services ergo frequency or voltage regulation, energy and congestion management, enhance steady state and dynamic performance of power delivery. The desired services to TSOs are enabled by appropriate coordination of storage assets, ergo pump hydro storage. When using STO-CC, storage owners will become active players in electric markets, maximizing storage revenue by energy arbitrage and delivering multiple services to the networks. Furthermore, the energy producers will use STO-CC for optimal dispatch of a portfolio of generating units. STO-CC market participation. On this and on the next slide, we will present the main application or user cases that can provide higher profits to the end users. The first application we'll talk about is the curtailment reduction. So when we talk about the curtailment reduction, we basically talk about the increment of revenue due to the reduction of curtailment, allowing to inject into the grid the major part of a non-dispatchable power generation, basically PV, wind, or some other kind of renewable generation. If we consider the assumptions 1 and 2, we estimate a income for curtailment reduction at 438,000 euros per year. Second on the list is energy time shifting. This service allows us to shift the energy from the moment of generation to the moment of maximum energy prices. Once again, if we consider the assumptions 1 and 2, we estimate the income of energy time shifting at 876,000 euros per year. On the right-hand side of the slide, a bar chart is presented where with colors blue and green, we graphically presented the curtailment reduction and energy time shifting function of STO-CC. On this slide, the remaining two STO-CC services are presented. The first one is ancillary service. Here, the storage unit will provide a portion of energy to support the grid instead of participating in the wholesale market. If we consider the assumptions 1 to 3, we estimate a income for providing ancillary services at 4,380,000 euros per year. Next service on our list is congestion prevention. This would mean a possibility to introduce flexibility into the system to the storage capacity with aim of preventing as much as possible congestion issues. So once again, considering the assumptions 1 to 3, we estimate a income from congestion prevention at around 438,000 euros per year. In the bar chart on the right hand side of the slide, we can see the ancillary service and congestion prevention presented graphically in the colors orange and yellow. On this slide, we'll present the economic assessment on the STO-CC tool. For this, we created a STO-CC cash flow estimation chart, which can be seen on the right-hand side of the slide. If we give a closer look to the chart, we can see that after the initial year, which is accompanied with high initial costs, it is expected that the number of direct purchases for the full platform will be reduced in the first years of the cash flow, but we can also see that we will have low variability and a steady incline in the later years, and we will average at 1 to 2 projects per year. This cash flow estimation is also backed up with assumption that with a high penetration of renewables in the future, which due to their intermittent nature tend to destabilize the grid, TSOs will favor STO-CC to decrease congestion and increase grid stability. Based on previous estimations and this cash flow estimation, the internal rate of return for STO-CC product is 22.4%, which constitutes a very competitive approach with a high level of interest for future investment or financial support in case if needed. Thank you.
Thank you for watching this webinar. You can visit our website crossbowproject.eu to find more information. Also, follow us on Twitter and YouTube.